Hey, in this video, I will try to synthesize in a really fast way how can we write the vector parametric and symmetrical equation of a general line in a space, okay? So to begin, I will represent a general line, and I'm just putting the x, y, and z axis here. And this general line, for example, I will call R. Great. And in order to write all those equations of this line, I just need to know two informations, okay? The first one, it's a point that I know that lies in the line, okay? Once I know this point, I will know the coordinates of the point. So I will call them x0, y0, and z0. I know those coordinates. And the second information I need to know is the coordinates of a vector that I know that the vector has the same direction of the line, okay? So let's suppose you also know the coordinates of a vector v that I will call a, b, and c. And I know that this vector has the same direction of the line. If you know those two informations, a point that it's in the line in a vector, that the direction, it's the same direction of the line, so you can write all the equations that we consider in this video, okay? So in order to write the equations, we can, for example, think of a general point, P, and we need to infer what are the conditions that this point P needs to satisfy in order to be in the line R. Okay, once I'm considered this P a general point, I will call its coordinates x, y, and z. Okay, and to this point, P in the line R, what it needs to happen? In this case, to this point P in this line, the vector AP, that it's a vector that begins in A and ends up in P. This blue vector here that I will call the vector AP because it begins in A and ends up in P. This vector here, if this point P it's really in the line, needs to be a multiple of the vector V. Remember that all the time you multiply a vector, for example, let's suppose you have a vector U. If you multiply a vector by a real number different of 0, in the end, you are just stretching or shrinking the vector. For example, if you have a vector u and you multiply the vector u by 2, you will have the vector 2u. Okay, that the size is twice as large compared to the original one. And if you multiply this vector u, for example, by 1.5, so you have this vector 1.5 times u, that will be the half of the original vector, okay? So if this P, again, belongs the line R, so means that the vector AP, it's a multiple of the vector V. So means that the vector AP, it will be equal AT times V, okay? So we can say that there is a number t belonging to the real numbers such that AP it will be equal t times v. Okay, once we know that the coordinates of a point AP, it will be the coordinates of the final point minus the coordinates of the initial point, the vector AP can be split it as P minus A being equal T times V. Okay, the coordinates of the point P, remember, are X, Y, and Z. Okay, so I will switch P to X, Y, and Z. And the coordinates of the point A, we know that they are X0, Y0, and Z0. Okay, and this needs to be equal the number t times the vector v, that we also know the coordinates, they are a, b, and c. Okay, and for example, if I leave the x, y, and z alone in the left side of the equation and send this point here to the right side of the equation, I need to change this sign here. This sign will become a plus. So x, y, and z, it will be equal x0, y0, and z0 plus t, a, b, and c. And this, it's precisely what we call the vector equation of the line R. Okay, very good. We already got one of those equations of the line R. Okay, I will continue from here. If I operate those vectors, those points here, the coordinates of the points, I need to do this coordinate by coordinate. Okay, so if I want to operate those two guys here, what I need to do, I will operate coordinate by coordinate. So it will be x minus x0, y minus y0, and finally z minus z0. And if I multiply a real number by a vector, I need to multiply coordinate by coordinate. Okay, so it will be at, bt, and ct. Okay, now we have that those vectors here, or those points, if you want to consider it's a point or a vector, it does not matter, they are equal. If they are equal, means that the coordinates needs to be equal. So we know that x minus x0 needs to be at. We know that y minus y0 needs to be equal bt. And finally, we know that z minus z0 needs to be equal ct. Okay, if we write this, we have that x minus x0, it will be equal at, y minus y0, it will be equal bt, and z minus z0, it's equal to ct. Okay, we have a system of equation here, and in each equation, I will send this term here to the right side. Okay, so I have that x, it will be equal, x will be equal x0 plus at, and I will do the same thing in the other equations. Okay, I have y being equal y0 plus bt, and I will also have that z will be equal z0 plus ct. Okay, those one here, guys, it's what we call the parametric equations of the line. Okay, parametric equations of the line R. Okay, very good. So we can also represent this coordinate by coordinate. Okay, so we can represent R as a line which the coordinates are x, y, and z, that the coordinates end up depending on t, so I can represent xt, yt, and zt here. Look, if you change the value of t, you change the point. Okay, so those coordinates, they depends just on t. Okay, they relies on t to change its value. So we can represent the line R as a line which the xt, it's x0 plus at. The second coordinate of the line, it will be y0 plus bt. And finally, the third coordinate, it will be z0 plus ct. Okay, you can represent the parametric equation of the line in this way as well, no problem. And finally, look, if I take this form here, I will copy and paste and put a little bit down here. I will drag a little bit down, and pay attention in this. Now, just okay, I'll just put here. Let's pay attention, guys. in this situation now, if you have x minus x0 being equal at, so means that we can write t as x minus x0 divided by a. If you have that t, that y minus y0 it's equal bt, so means that t, it will be equal y minus y0 divided by b. Okay, I'm just setting this b to the other side divided because the b is multiplying the t. Okay, and I will use the same strategy in the third equation, so I can write t as z minus z0 divided by c. Okay, but if you know that t is equal to this, and to this, means that the right side of the equations, all of them, they are equal because each right side of the equation is equal to t. Okay, so we can write that x minus x0 divided by a, it will be equal to y minus y0 divided by b. That will be equal z minus z0 divided by c. Okay, this last form here, it's what we call symmetric equations of the line R. There are important informations regarding the symmetric and parametric equations. Okay, I will go back to the parametric here and just highlight that when you write the parametric equations, this column here, it will be a column that will be exactly equal to the coordinates of the point A that you know in first place. Okay, remember I told you need two informations, a point A and a vector v. The coordinates of the point A will be the column that appears here in the parametric equation of the line, and we have a second column here, and the second column that will be the numbers that multiply the parameter t. It will be the coordinates of the vector v. Okay, and those guys appear in the symmetric equation as well. Okay, as you can see, the numbers x0, y0, and z0 that appeared in the symmetric equation means the coordinates of the point A. Okay, and the denominator here, a, b, and c, means the coordinates of the vector v. Okay, so those are the vector equation of the line, the parametric equation of the line, and the symmetric equation of the line. Okay guys, I hope you enjoyed this video. Bye bye.